We're going to talk a little about garbage collection and how we can calibrate garbage collection. I've been before to VDCLUJ, Romanian, and I'm happy to be here today with you, Omana, currently working as a developer advocate for Oracle, and looking forward to having this presentation towards you. We're going to look at a little bit of theory. We're going to look at why does garbage collection calibration matters for us as developers, why we should look into it. And of course, we're going to see the setup of what I compared and how I compared different calibration for my applications. And of course, we are going to look at the comparison between different garbage collections and the results that I got. So why do we love garbage collection, especially in Java? Because, well, obviously automatically frees memory for us. And if you have tried other programming languages, probably in the beginning when you were in high school or in university, you've noticed that you had to like malloc, clog, and all the time work with the memory yourselves. While on Java side, that is performed for you automatically. Now, garbage collection, in a nutshell, deals with memory management for you, and has a few advantages. For example, well, it allocates objects on the managed heap efficiently in case of Java. It reclaims the no longer used objects, and it clears their memory, so keeps the memory available for future allocations. Now, an important part about garbage collection in Java is that it's generational, so it means that, well, the garbage collection primarily focuses with reclamation of short-lived objects. Newer objects have shorter lifetimes, older objects have longer lifetimes. And of course, the newer objects tend to be related to each other and accessed during the application runtime about the same time. Now, to optimize the performance of a garbage collector, the managed heap is divided in 3 generations, 0, 1, and 2. So it can handle long-lived and short-lived objects separately. Now, the garbage collector stores new objects on generation 0. Objects created early in the application's lifetime that survive collections are in generations 1 and 2. And of course, we have a few types of garbage collectors. Some of those garbage collectors are unigenerational. The other ones have 2 heaps. And probably, if you worked with older versions of Java, you've used CMS quite a lot. I put here in the slide that it was removed since JDK 14. And well, some of the developers also asked themselves how we can move to other garbage collectors, and hopefully the presentation of today will give you a clue about that. Now, why does choosing a garbage collector matter? Well, first of all, it matters because collectors, all of them, strive to be as optimal as possible from every aspect, meaning they are designed with different trade-offs to support different use cases. And you'll see that in the applications that I have as well. So a few questions have to be in your mind when you're thinking of fine-tuning the garbage collection, or maybe if you should do that. And some of them is like, do you get the performance that you want? Secondly, are the GC poses that you currently have maybe as defaults working great for you? Maybe if you're having that as at a higher amount, you get more latency, or if you get them a lower amount, you get more throughput. And of course, can your application tolerate some full GC pauses? So these are the 3 questions that you have to ask yourself when it comes to fine-tuning garbage collection. And the performance considerations when it comes to fine-tuning garbage collections, probably they're known to you, are, I would say, 3 of them. Like throughput, first of all, meaning the total successful transactions that your system can do. Latency, how fast did you get those responses? And of course, footprint, like how many resources is your system working on? And of course, all the time we're going to strive for like a perfect match between all these. Like we want the best throughput, the latency to be as decreased as much as possible, and of course the small memory footprint. However, as I said, it comes with trade-offs. And another question that probably is coming to your mind, like, is my application more CPU intensive or more IO bound? So what kind of resources does it use more, and how is that connected to the garbage collector that it uses? So some CPU-intensive examples, just to give you a clear view of what CPU-intensive means, is, well, a type of problem that requires a lot of processing power to solve. So CPU-intensive has to do a lot of work, computes a lot of data, without ever waiting for new data to arrive. It just keeps going, you know. And IO-bound, on the other hand, means that a given task often awaits for I/O. So, for example, networking, working with file I/O, and so on. Those are slow, and they're not compared to the CPU application. So, when the CPU has to regularly wait for data to arrive, the task is said to be IO-bound. So let's look at our setup. Well, my setup. I use two applications. Well, one is called eager factorial, and what it does, it eagerly calculates big factorials using big integers. From my point of view, it's a CPU-intensive, CPU-intensive operation to calculate big factorials, like for factorial for 2000. It's quite a lot struggle to mathematics to be there. Second one is continuously editing a file for a while, so it works a lot with the file system. The way that I tested these applications, I used some K6 tests that I ran them in TestCube. So that I want to check how my applications perform during a certain amount of time, when they receive requests for a certain amount of users, and see how garbage collection was improved when tuning it or not, or which aspects of those were fine-tuned. Now, I said that we need to observe the applications, so I need a way to observe the application throughput, and I can do that, of course, with PromQL query. Now, for my application, the app request duration seconds count is giving me that, and I'm getting the rate for that specific amount. And then I need a way to measure the latency, and that's the query in Prometheus that I used for that as well. Now, for observing CPU and memory, I've used these two queries because I want to see the increase in time series in the range vector of CPU usage query. And of course, I want to see the average over time of memory used query. So let's see if this works. I'm trying to see. Okay, good. So the two applications, just to see them, well, first of all, they're running on JDK 21, but they use no framework. So what I did, I want to keep them simple. I didn't want to look in a particular framework. And I created my own server using HTTP server. It's in Java, it's an allocation. It performs the mathematical operation in case of the continuous editor, like editing continuously. And because I need to export my data, I just used the micromatter registry Prometheus and the simple HTTP server to create my own way of, exporting metrics for Prometheus. Furthermore, the deployment, there's, okay, one sec. The view of Kates is like how they're deployed. So this is how I'm starting with the default deployment for my application. And of course, because I want to see which garbage collector is used and maybe what's the default startup for that, I log to a file called tmpgc.log, which I created previously using an init container. And the tests. Now, both applications will run the same type of test. In the case 6, because I wanted to see results quite fast, I say okay, during 30 seconds, I want 80 users to try to send as many requests as possible to each of my application. So it's a traffic ramp up. It raises from 0 to 80. And these 80 users try to do as much as possible during those 30 seconds. Now, for the next 60 seconds, the 80 users, again, they're trying to do a lot of work. And then after this 1 minute and a half, everything lowers down to 0. So pretty much see how my application behaved in this. The same setup is in both cases, so I try to keep it easy. Now you see here some summary trend stats. I want to see the average of my requests. But I also want to know the percentile 95, meaning how how my 95% of requests performed. So what's lower than the 95%, like the value of 95% is the maximum for those 95% of requests. What's the 5% extra is above the P95 that I see there. Same for P99 and P99.99. So I want to see how that happened for the majority of my requests as well. And in the case of my setup, as I said, I'm using case 6, and I have a test suite that runs both of my tests. And if I'm looking at the tests here, you can see that I have the factorial tests and the continuous editor. What this does is that when I'm running the suite, both of the tests are run in parallel. So I can record that in Prometheus for my queries, their performance in parallel. So I'm not executing them sequentially. This is quite useful of that. And of course, the output is in each of the K6 parts. Okay, so let's start with the first garbage collector. Serial garbage collector. So in case of serial garbage collector, for my tests, I haven't used it. And I can explain why. My application by default starts with 2 cores. And the serial garbage collector, historically speaking, is the default collector in case that my application would have had a single core and would have used memory up to 1,792 megabytes. Now, this collector is useful for these kind of single core application that use up to 1,792 megabytes. So it's best suited for single processor machines because it can take advantage of the multiprocessor hardware. And, well, it's a great collector if you want just have like applications that have small data sets up to 100 megabytes. I've seen people saying like, yeah, this is the default for my application. We can talk after this talk about it. I just didn't want to force my application to use it, as it would have been an overkill to like, underperform it by default, since this was not the first option for it. It was the first option for none of it. Now, first G1 garbage collector. This was the first garbage collector that was selected by default by both of my applications. How this one works, the G1 garbage collector divides the heap into smaller regions. It works with these smaller memory segments to mark and sweep them. So it keeps track of the amount of the reachable and unreachable objects per memory region. Now, the regions that are most unreachable are first garbage collected, and so that means that it frees most of the memory. That's why it's called garbage collector first. And, of course, why it works great by default. So why it was selected by default. Besides the fact that my 2 applications start with 2 cores and use more than 172 megabytes of memory, that made them like choose this for garbage collector first. This one works great, besides what's written in the slides, because performs the part of all generation space reclamation concurrently. So that's why it's one of the first to go. Also, it tries to meet the pause time targets with high probability over a longer time. But you don't see all the time the same pause. How are the test conditions? So the test conditions, when I started with nothing, just logging what's going on in my applications, I looked over what happens over there in the gc.log, and I could see that the maximum pause time was set to 200 milliseconds for my application. And well, the test condition in both cases was that the traffic ramp up to 80 users over 30 seconds, stay at 80 users, and then ramp down. How are the results? Now, the results in this case, I'm going to look over. Let me see if this works. So I'm going to look over HTTP request duration line and HTTP request failed. I'm interested in throughput, like how many requests I got, what was their average, what is the percentile 95, percentile 99, and percentile 99.99, and compare that. So for latency, I got some results, and I got an average of 84.17 milliseconds, but for Cell 95, it getting closer to 1 second. So this means that 95 of my requests are closing to 1 second. And of course, in case of requests that of throughput, I just got a 6,688 requests for the 80 users. And also, I'm giving you the explanation on what the request duration rows means. The expected response through is like, if you have errors like 404 and all these kind of things, you're going to see slightly different error values on the upper line, while the average expected response through is always going to tell you like these were successful all the time. This was for the eager factorial. So eager factorial was my mathematical app, was the CPU intensive one. The one that is file I/O intensive got some similar results in terms of like throughput, almost 6,689 results, and similar results in request duration in average. And percentile 95 again is closing to 1 second. So, increase of CPU usage. Well, as expected, the eager factorial is using a lot of CPU, while the continuous editor that's like I/O, it has like a flat line in CPU time. In case of memory, well, again, as expected, the editor consumes more memory, while the factorial consumes kind of flat at some point. But I want to improve these results. So I'm thinking of tuning it. And first of all, I'm saying like, hey, I want to improve the latency because those 84 milliseconds kind of bother me. So first thing that I'm thinking of is like, okay, maybe I can set a lower pause time for my garbage collection. And that would make the response more eager than it was. And let's think about how we can do that. So I thought like, hey, let's try to put that to half and see how that would work. So I started by doing the G1GC allocation with a reasonable pause target. Now, don't go to 10 milliseconds because you will see some unexpected results in terms of throughput, like even less throughput. And in some cases, I signaled here, like if you're having like unusual real-time system usage, like the VM is allocating or giving back memory from the operating system with some delay, you can avoid that delay by setting the minus XMS and minus XMX with the same value. Probably you've heard this before and seen people setting the same value all the time. That's the reason why, so that you avoid that unnecessary delay. Now, in case that there is additional CPU available, you can adjust the number of threads using the minus XX conc GC threads. So that's where you see the second option there. Obviously, in case of an application that's CPU intensive, you wouldn't want to do this because, well, you're thinking like, that's already CPU intensive. I just don't want to like work over more. But if the CPU is not that overworked, you can, and you're thinking of the memory intensive one, you can just use the minus XX conc GC threads. So the main idea of this is like the maximum pause times should be at a reasonable value, but in some case of some application, you can increase the throughput of that application if you decrease, if you're using the minus XX use large pages. So that's another thing that you can do. And another trick for throughput would be to set the amount of concurrent work minus XXG1 rset, updating pause time, pause use time %, I think it's the flag. So let's see what we improved. And I have the first one, like the default, and then we have the second, after we improved the max GC pause time for the one that's CPU intensive. So if we're looking over this, after running the test, we can see that, of course, the average request time, it decreased like almost 30 milliseconds. So I improved my latency. But not only that I improved my latency, if I'm looking at the count of my requests, those were improved. I think I have like 300 more requests that reached my application. Of course, latency improved. The responses were served more eager, so my other numbers got improved as well. That's great for the one that's CPU intensive. So just by setting the max GC pause millis to half, I managed to improve both my throughput and my average request duration by, I think, 20%, something like this. Now, in case of the application that's more I/O bound, the improvements are also there. So if I'm looking at the improvements that I've done with the parallel GC threads and conc GC threads, because I knew that this one had CPU available, so I could say like, okay, I can use the XX conc GC threads. I'm looking at the latency. I got an improvement of 4 milliseconds. It's good. And I'm looking at the requests, and throughput is lower. So I got some improvement, but probably I could do better, or I could do more for my application that's I/O bound. Now, if I'm looking at the increase of CPU usage, not much has changed. So the CPU usage stayed sorry. Damn it. Okay, so the CPU usage stayed the same for both, so not much change, but in one case, the latency and the throughput increased, while the average memory over time, in some cases, it got even lower. So overall, the remarks were that I got some latency decreasing and throughput increasing for my application that is CPU intensive, with the G1 GC application after improving after fine-tuning my flags. And then I got the latency decreased and throughput slightly decreased for the one that's I/O bound. But I like that more requests were served by my application that's CPU intensive with a higher latency, with a lower latency, while keeping the same memory and CPU consumption. So overall, I'm pretty happy with the current setup that I got. And on the other hand, the one that's I/O bound, well, uses less memory, so still a win. Can I do better? Let's try another garbage collector. So for example, the parallel collector gives me a few advantages as well. So the parallel collector is called the throughput collector. So if I want to strive for more throughput, I'm going to think of using it. However, it's not just for throughput. The parallel collector has 3 goals. The goal is to have maximum pause time goal, throughput goal, and minimum footprint goal. And these 3 goals are addressed in order. So the garbage collector, the parallel garbage collector tries to meet the maximum pause time goal first. Then it tries to meet the throughput goal set, and the last one is the footprint goal addressed. So this collector has a certain way of working in terms of selecting its priorities. Next, why it works so great. So a lot of people use parallel GC for their application. You can see testimonials on the internet. The parallel GC is the best for their application. Well, it works this great because it has adaptive sizing within the heap and generations in order to meet the pause time goals. And well, as well, you can see that it has a clear definition of throughput. So you can control the throughput that you want using the GC time ratio. So it's something that you can control and you can calculate mathematically for your application, which is pretty cool. Now, it's great because it has the adaptive sizing in throughput collector, which will resize the heap. But also it's great because it can do growing and shrinking of size of generation incrementally. And you can see the flags by how this can be controlled. Now, in case of my tests, I had to enable manually the parallel GC. So I had to use the parallel GC manually. And, of course, I had some same test conditions over it. So let's see how things improved over this one. Just the default, no fine-tuning over the parallel GC. So if we're looking for the results on the eager factorial, remember that earlier we had like 80 milliseconds something for the average duration of my requests? Now, in this case, we have an average duration of requests of 4.8 milliseconds, so that fast. And of course, because we have served that this way, we get more throughput. So overall, it seems like best results by default for the CPU intensive application. Now, using again the default for the one that's I/O bound, we can see that there's an improvement in the request duration there as well. It's lower, and of course, more throughput. So that's a win-win for both, apparently. If I'm looking at the increase of CPU usage, not much has changed there. So just changing the garbage collector, I get the same usage of the CPU in both cases. And in case of memory, I can see that my eager factorial is slightly more memory consuming, but the one that it's file I/O bound that I expected to consume a lot of memory starts to use less memory as well. So the intermediary remarks in this case are that, well, I have the latency decreased and throughput increased in both cases. Memory CPU usage, well, decreased for the one that is CPU bound, and, well, the one that's continuous editors is doing way better as well. But I want to fine-tune this. I want to get even better results. So let's see if we can make it even better than this. We can make it even better than this by adjusting the pause time, like we did it the other time as well. And adjust the throughput for the continuous editor, because maybe I can get more throughput for the one that's file I/O, more requests served by that one. So after running the improvements, let's see what happened. So first of all, in case of eager factorial results, I got a decrease in the results of my latency. So latency increased while throughput decreased. And some of you will be like, oh my God, that's not good. But we're going to look at memory and CPU afterwards. And in case of the continuous editor, on the other hand, with file I/O bound, we get a significant improvement in both latency and the throughput. So that's a win. Now, the CPU usage is pretty much similar, but the memory usage, in terms of like of eager factorial, it's lower than it used to be. So overall, the remarks would be that in case of the eager factorial, the memory usage and latency are lowered compared to G1 GC results in any case. But throughput increased also compared to G1 GC results. I have a slight memory decrease in case of my eager factorial, and that's a win from my point of view. Now, continuous editor, the one that is file bound, significantly sees improvements, like in latency decrease, like in memory usage, like the throughput increased, and of course, memory usage also significantly decreased. So it's a great win for me as a developer and in terms of runtime used. Now, the last one, because I want to get even better results and see if there's any other better option for me, I'm going to look at the Z garbage collector. Now, this is a garbage collector that many of us probably don't think of using. It's newer than the others. And it works a little different and is recommended for different use cases. So for example, in case of ZGC, during compactions, objects move their position in memory. And what happens is that ZGC is looking first at having these pause times as small as possible. So that's why it has those goals like sub-milliseconds max pause times, but it works best on large heaps. So if you're not having large heaps, probably you're not going to see the same improvements. Now, ZGC was initially introduced in JDK 11 and made GA in JDK 15. So there are a few things that you should know about ZGC. It's a concurrent garbage collector, meaning that all the heavy lifting is done while the Java threads continue to execute. This greatly limits the impact of the garbage collection that will have over the application's response time. Well, you can see here all the characteristics of ZGC, but you can also enable generational ZGC that was made G8 in JDK 21 for a reduced effort to collect garbage. And you can enable it by using the -XS plus Z generational flag besides the UZGC. Why you should do that? Because it comes with some automatic tuning. So you don't have to do any more XMS configuration or specify any concurrent GC threads or number of threads there. The only thing you need to specify is the -XMX, the amount of the heap that you're having to use it. So in case of the test conditions of the GenZGC, I just started first with the UZGC to Z generational and see how just the default, how it works. So in this case, the first results, in case of my application that is CPU bound, I got a slight increase in my throughput, and of course, I got some values for the duration, for the average duration on this one. However, when I'm moving to the one that is using more of memory, so it should have like a larger heap size, I can see that in this case, the throughput increased significantly while the average duration location is lower. Again, if I'm looking over the increase of CPU usage over time, I don't see many changes. While I'm looking over the memory, I can see that more memory is being used in this case. However, I get better results on latency and throughput. So, if I want to fine-tune this, in case of my application that is more CPU intensive, I'll use the -XX use large pages flag to commit eagerly the large pages in memory. While in case of the continuous editor, I'll just keep the -XMX flag there. So if you're wondering, by the way, how did I choose the amount of memory that I'm using, I chose that based on load tests on my application and saw like what's the upper memory usage for my app, but also looking in the gc.log to see how much memory is being used throughout time when there's intensive work on my app. So that's how I found that out. If I'm looking over the eager factorial results after fine-tuning, I can see that it's way better. So far the latency is the lowest in this case, so the CPU-intensive one, I have the lowest, I think, latency, and I have the highest throughput thanks to that, which is great. Now, if I'm looking to the one that's I/O bound, on the I/O bound case, I can see an improvement as well on latency and an improvement on the throughput. Now let's look at the CPU usage. CPU usage is slightly higher. Memory is lower. So compare the first time when I didn't set any memory bounds, now this time it stayed in some boundaries. Let's look again at what we had and how things worked throughout time in the comparison. So we started with defaults. And in the default part, we have started with like an average request duration of 84.17 milliseconds, which was the highest with the G1GC, the default for my application. So in case of the first application, the one that does mathematical calculations, it's CPU intensive, G1GC, the default was not the best that I could choose for it. Of course, I can fine-tune it, again, get better results, some throughput increase. But just moving to parallel GC, I can see that I get more throughput. And if I'm like looking at the other options for my GCs, I can see that I can get the best latency using ZGC. So the question is that you have to, put yourself when you're trying to choose a garbage collector is like, what do I want? Do I want for my application to have the lowest latency, or do I want for my application to have the highest throughput? If the answer is throughput, most of the time parallel GC is for you. If the answer is latency and a slight decrease in throughput, ZGC is the answer for you for the CPU and for the CPU-intensive apps. Secondly, for the one that's intensive, file I/O intensive, if we're looking at the results, again, the default was not the best for it. Fine-tuning it helped, especially in the percentile 95 part. It's like 10 times less. But I got the best results when I fine-tuned parallel GC. So I got the average result for my requests better here in the latency for the parallel GC. And of course, the percentile 99 is here the best. While if I'm looking on this column for the ZGC, I get the best throughput when I'm using ZGC. And of course, the percentile 95 looks best in this case. Now, if you ask me personally, I would prefer an application to have like 95% of the requests lower than 8.58 milliseconds and have higher throughput than just aim for an average that's slightly lower and have less throughput in this case. So these were pretty much my results. This is where you can find the code and the tests for today's presentation. And I'm going to share those slides with you so you can get also the links that have like links to documentation and where you can investigate more about the garbage collectors. There is more in the ergonomics of GC tuning than that I showed to you, but I hope that this presentation will enlighten you on how you can look at tuning a GC from, let's say, real-world perspective that you're having in your applications. Also, I'm aware that applications don't have a single dimension, like it's CPU intensive, it's IO bound intensive. So most of the time you're looking at it using some CPU, it's using some memory, so you don't necessarily choose just one side, you just want the best. However, as I explained in the beginning, you cannot have everything. You have to make some choices and some, let's say some just think that, well, if you have like higher throughput, maybe latency will be affected a bit, or you can have like, let's say, better latency, less memory footprint, but less throughput. And every application need is different. Thank you for listening to me. I'm looking forward to have your questions and to talk more with you after the talk. Thanks. If there are any questions, I can answer to you. Sure.
So, did you run the test multiple times? Because I saw that in the last test, so the IO intensive one, the throughput was very similar to in the ZGC with the parallel one.
Yes. So the question was like if I ran the tests multiple times. The answer is yes. So I ran the tests multiple times because I thought that because in the continuous editor file part, since it's edited continuously, the file size increases. So I'm expecting that it will take a longer time to read the file, for example. So I needed like an average of how that is dealt with. So I did run the tests multiple times, and I chose like some results that were relevant for the app. Like when I saw that the response is kind of similar, like it's 0.001 millisecond difference in the percentile 95 or in the average request time. I said like, okay, it's probably stabilized here, and that's it. It's way easier for the CPU one because it just calculates randomly some big numbers. And I could always get the same result in that case, but in the other one that's file bound, since the file size increases, it took me to like, I think I ran them like 5 times in order to like get some conclusive results on that. So that I don't feel like, okay, in the beginning when the file size is lower, maybe I get better results on my application. And then when the file size increases, I get worse results. So yeah.
Which Java version you used, and do you think there are differences between various JVMs?
So for my presentation, I kind of went a little fast. I used JDK 21, since it's the latest one. Also because in JDK 21, you can see the generational ZGC, like have it GA. In the previous versions, it was experimental. And yes, I can see slightly improvement performance between the runtimes through each Java release. And it's, I think it's kind of, let's say, proven that performance of the runtime gets better and better with each release. It's something that is worked under the hood for us Java developers as well. So it's not just nice language features, it's also better runtime performance as well. And also, if you look at the links that are here, the blogs on ZGC and all the other collectors, sometimes they refer to the performance improvements there as well. And if you want, like, let's say, something that's not done by engineers, Geoffrey Desmet has a blog on how his application, it has a real-world usage, benefits from JDK, moving to JDK 21 garbage collection. So he uses the same garbage collection all the time throughout Java runtimes. He didn't change much code in their application, but just by changing the runtime, he got better performance. And I think he had a deep dive at DevOps Belgium on this, on the improvements that they saw throughout time for their applications as well. But I can give you the link after the presentation too. So that's more like, let's say, real-world testimony that it works and it's better. But one thing that you need to know, his application is focused on throughput and does mathematical calculations. So it's similar to eager factorial, where in that case, parallel GC was always the best option, at least from my point of view. And in his case, also parallel GC is the best option, because he does a lot of mathematical calculations in its app. Any other question?
Yes. In my head, lower latency should lead to higher throughput, but we could see that that was not always the case. What is impacting the throughput? And
ideally, yes, lower latency in average should get us more throughput. However, I just ran the tests and I haven't seen, for example, I think that probably some of the tests that were on 99 or 95, those 5% over the 95%, like affected the throughput that I saw. In my case, I think I saw that some requests took longer to complete when there was a higher load on my system than in the other cases. And I kind of trust K6 for its results. So yeah, that's the case of that. Also, although that in some cases I worked with the GC pause time, so it's lower, my system still has to work and do the work. So just forcing your system to have like lower pauses when doing work doesn't mean it doesn't get tired at some point to do something.
And the second question, for a usual or normal web application, which I guess it has more I/O-bound operations.
Yes.
Which one do you use in production?
I don't have a general answer for this, for the regular application. So I've tried several tests on different frameworks, for example, on Spring Boot and on Quarkus, and I saw different behaviors. Also, as I said, in real life, it's not just one way of working. So it depends a lot on the framework that you're using as well, because that one is impacting how your GC works as well. But also like what you try to tailor within your application. In my case, I kind of choose, okay, that one is CPU, that one is I/O bound, I know which one does what. But in case of web applications, most of the time people see CPU usage and memory, and it's the same because they use probably one framework all the time. So I don't have a generic answer, use this all the time. I can say that most cases, parallel GC gives you better throughput, for example. Also, if you're not having like large heaps in that case. If you're having large heaps, ZGC works best, gives you the best latency, and probably the highest throughput. But again, the key is like having a large heap working there. It's not like every case, it works the same, it works the best.
Thanks a lot.
Welcome.
Saying large heap, from what size are you referring to?
I had it in my slide from... Yes, from, handle heaps ranging from 8 megabytes to 16 terabytes. But in the case of my applications, for example, I got the best results on Continuous Editor, but Continuous Editor used 2,816 megabytes. So that's when I determined that it's using, that would be the best memory that I can set for that one, for it to like give me the best latency and also throughput. But it used more memory than in the other case. So if your goal would be all the time keeping memory as small as possible, maybe looking into other garbage collector would be better. But if you're thinking all the time of serving requests, because, well, most of the time nowadays in cloud, memory and CPU is cheap, then ZGC works best. You have to think of like what you want to serve first. And there are applications, like for example, banking applications, where your goal is to serve the requests of the user as fast as possible. And you don't think, okay, memory probably can be spared or CPU, but as long as the user is happy on the other side and the transaction happen in an instant, you're happy with the end result. Any other question? Yes?
I noticed for when you decreased the time pause from 200 to 100, that there was a huge spike in the 99.9% on the latency. And I was curious if this is a regular behavior or if that just happened, like, because if it is a regular behavior, you kind of have to know that trade-off.
Again, it depends what you mean by regular behavior. If regular behavior in case of my application that I used as an example,
yeah.
Yes.
Yeah. Okay.
So yes, I can speak of these examples. All the time, like when you're trying to measure something, measure it regarding you and what you're building, not what others built. So in case of my application, yes. Because as I said earlier, I ran multiple tests, so... And by the way, I also ran multiple tests hoping that things are improving, or like if more, I don't know, more intense operations happen over my application, then I can see a significant difference, or there's a significant difference within what I'm doing. Or I can, like, I don't know, fine-tune my load tests also. But in case of my application, yes, it's always the same result on the P99, P99.9. However, you have to think like, look at P95, because that means like 95 of your requests will be lower than that, lower or equal to that. And then look at the 99 one. Just looking at the 99 one and seeing a big result might scare you, you know? But if you're looking at the 95 one, and also in the presentation, if you look on the 95 compared to P99, you're going to see a significant difference between them. So this means that those 4% between 95 and 99, probably they took longer to execute and deliver a response. And again, the question, can you live with those 4% taking longer or not, while the other 95% are doing well? Any other question? Yeah.
Did you also try it with different contexts, like, I don't know, higher number of users or an extended amount of time to compare? Because
so a higher number of users and a higher amount of time?
Yes.
Okay, so I tried the test for a higher amount of time and also a higher amount of users. And yes, the results were similar, by the way. The only thing that bothered me was the amount of time that the tests were taking, because spending half an hour, and more time on this for each situation took a lot of my time. So that's why I kept it to 2 minutes so people can see that. Secondly, if you're running these tests on local, because K6 is something you can run on local, let's just say that my internet provider saw this as something that I was doing within my network and thought that it was an attack. So, for example, I didn't have internet for some while at a good performance first, and then I didn't have internet. So be careful what you're doing with that on local. But yes, I did run it for a longer amount of time and with more users. And if I ran it with a lot of users, I think initially I said it like 500 or 1,000, I could crash my my application because it was out of memory and so on. So, and that was not, let's say, not what I wanted. I just wanted to see how well it performs during an amount of time, reasonable amount of time for an amount of users. And the important part is not, I wouldn't say the amount of users, but the amount of requests it can serve. Because this is like, say, an experimental application. Somebody didn't tell me, like, we're going to have this amount of users, and it has to perform better. Like, if in real cases your customer tells you, like, we're going to have this many users, do your best, yeah, you can adjust the tests for that situation. Also, in the K6, there are multiple ways to run your load tests. So just sending as many requests as possible is one way. But you can also have like requests sent in parallel by the users and, you know, just have a fixed amount of requests. In this case, was like competition of doing as many workloads as possible, not having as many users as possible.
Understood, thanks.
Okay. If there are no other questions, we can meet in the hallway as well. And I can tell you also how you can determine the flags in a different way in the conversations later. Thank you, once again. Great questions.